So, this talk is sponsored by the Central Virginia Node of the Commonwealth Cyber Initiative. We're a state program establishing Virginia as a global center of excellence in cybersecurity research through supporting research, workforce development, and innovation at the intersection between cybersecurity, autonomous systems, and intelligence. And each year, CCI and CVN sponsors research and experiential learning projects, and today's speaker is a recipient of that funding. So today we have Jayasimha Atulasimha, and he is a professor of mechanical and nuclear engineering at VCU and also the associate director of research and innovation at VCU's Institute of Sustainable Energy and Environment. He has a master's in science and a PhD in aerospace engineering from the University of Maryland, College Park, and has research expertise in straintronics, nanomagnetic devices, and neuromorphic computing. And today he will be sharing his insights on low resource edge hardware, auto encoders for anomaly detections in smart city networks. So I will let you take it away.
Hi, thank you very much for the introduction. I'm Atul, or at least I go by the short form of my name, Atul. I'm in mechanical and nuclear engineering. I also have an affiliate appointment at electrical and computer and physics. Today, I'm going to talk about edge AI hardware, and towards the end, we will specifically look at anomaly detection in various urban environments. That's the application. So, since the project is a very small part of the talk, about the last 10 minutes, I want to give you a bigger overview of the overall edge AI hardware. So, when we say that, what we want to keep in mind is we want to have a small chip that is doing inferencing increasingly on the edge without communicating with the server. There are two ways or two approaches. One is you think long term, can I develop that capability in the next 10 years? In which case, you can do more exotic things where you can have memory elements called synapses storing information on these very tiny nanoscale devices, and then hope that you could integrate that with existing CMOS or transistor technology where you are going to be able to do the neurons. And in other instances, you can do more complex things like reservoir, where you can have a sequence of time sequence and you can kind of classify and predict based on that, where you can use very novel properties of magnets, nanoscale magnets, and other magnetic materials. These are what I would call long-term, more researchy fundamental solutions, which are hardware AI, which have a lot of promise, but they are much further off. And then you can use existing hardware today like FPGAs and microcontrollers and computers and say that I'm going to find a way of using that with very minimal resources on the edge. And that's what I say as existing hardware, right? So my talk, I want to cover or encompass both these topics, this from a more fundamental research point of view and this from a more applied point of view. So I will present this first and then towards the end go into this area. So first, an introduction to my lab. I work on a lot of topics. Typically, they have all been using nanoscale magnetic devices, but have been focused on the area of computing, right? Which is different from some of the CCI work that I do, which is more about just hardware AI on the edge, which do not really involve magnets and spintronic devices. So if you look at the general problems of computing today, one is what's called non-volatile memory. Non-volatile memory is if you have information that you put, it is, let's say, the zero state and the one state, and you store that information forever without requiring power. You already do so in solid state devices, SSD memory, and hard disks, where you write information, it's there forever. But when we say non-volatile memory, we are very specific to that a random access memory element should be non-volatile in the sense you can write information in your chip, in your computer, in your CPU, and not lose that information while you're doing computing. Now, why this is important just goes beyond standalone non-volatile memory. It becomes interesting when you're doing hardware, AI. So you have in AI, a lot of tasks are matrix multiplications. So if you can give a voltage from this network and then multiply it by conductance or weight of the synapse, then what you get, the current that will flow already does the product of these two numbers. And if you can add these this output times this output times this weight, and so on, and sum all the currents, then what you're getting is in hardware, you're kind of implementing this matrix and a vector multiplication. So that is where you could also use these non-volatile memory devices. Only caveat is there, unless you're doing binary weights, you cannot have just 0 and 1, you should have multiple states. So this is where this non-volatile memory goes into classical AI hardware. And you could also do other tasks, which I said, like reservoir computing, which I will go into later. And then finally, our group also looks at using magnets to produce local magnetic field with which they can control NV centers and spin qubits. And that's what I talk about quantum control. But in this talk, I will not talk about my material science work or about the quantum control work. I will focus exclusively on classical AI hardware using nanoscale devices, and towards the end of the talk, anomaly detection. Right. So with this, I'd like to also acknowledge all my students. So I have a lot of students working on these diverse topics, but the students that are very focused on the hardware AI, both using existing hardware and magnetic devices, are Walid, Shabir, Sadi, and Lawrence. And I have also other students who are working on more material science and other or magnetic devices project, but also support some of the hardware AI, and that's Mahadi and Fahim. Um, so the talk will be structured as follows. We will look into why we want to do energy efficient computing at all, and then look at neuromorphic computing based on nanomagnetic devices, which is what I said is more basic research 10 years down the line for implementation. And then we will look at existing hardware that you can use, like your computer or an FPGA, to do edge computing. And this is very specific to anomaly detection. And then we will summarize and discuss future directions. So if you look at the cost of computing, it's not emphasized yet, but it is enormous. So one Google search costs you a kilojoule of energy. So the 2 trillion searches that happen every year cost nearly 2 trillion kilojoules of energy. A better way to visualize it is Google, which does most of its work based on computing, in 2019 alone consumed more energy than some countries with population of about 20 million. And this is increasing exponentially. So you can see very soon that when you talk about the energy usage in our society, it's not as much transportation that is going from one place to another is going to take energy, going to lead to emissions, I mean, carbon emissions, etc. But that's not the only factor. Increasingly, the act of computing, whether it's something like you look at a phone and you do a Google search, or and all these things are going to start consuming so much energy just because of the volume. And so it's a societally important problem to make this computing energy efficient, especially the AI tasks, if you want your computing to be sustainable. But there's another reason why we are interested in computing taking very little energy, and that's edge application. So if you're thinking of an implanted processor or something like that, then you don't have much energy or hardware resources available to you at the edge in this biomedical device or an IoT device. And that's where you need to be able to do your AI on very constrained environments where both the hardware and the power is constrained. And you can already see the number of applications where you have edge devices where you preferably don't want to communicate with a server and do the computing online. For example, in a self-driving car, you want to do that computation in the car, not transfer it somewhere else, right? And then you also have challenges there. As I mentioned, that the energy or power available is very limited, and your hardware resources are also limited. So next we go into this more long-term solution where we see there's a promise for benefit by integrating these nanoscale devices, which are like memory elements that store memory without requiring power or have very rich physics that can be used for computation. So with this, I'll briefly explain the problem of neuromorphic computing and then see where these nanoscale devices may be applicable. So if you look at neuromorphic computing, as I mentioned, what is happening here is there's a neuron that fires, and then the output of that neuron, the output of this neuron, all these neurons, if it's a fully connected layer, are being multiplied by weights, which are called synaptic weights. And then so you have this neuron multiplied by a weight coming here, this neuron multiplying by a separate weight, and then going here, another neuron multiplied by this weight, and then all these are summed to give the input to the next layer of to a neuron in the next layer. So that's what is happening. X1W1, X2WK2, and so on. All these are summed with the bias added to it, and that becomes the input to decide whether how this neuron responds, right? So doing this kind of operation takes a lot of compute, because you get this information, then you do the multiplication, then you store the output somewhere else. So this requires constant shuttling between the processing and the memory, right? And if you could have a memory that was local, and you could do computing around that locally stored memory, very much like your brain does. You have neurons, you have synapses, and that all connects to the next neuron and so on. You could be much, much more energy efficient at the hardware when you implement it. And that's why it gets the term neuromorphic computing. And there are many such nanoscale devices which could store weights. And since I come from a magnetic or a spintronic devices background, we use magnetic devices as an example for our ideas here. So let's understand how these magnetic devices behave. So if we have this magnetic device here, which could be small, it could be a micron, it could be even half a micron, much smaller. The width could be 50 nanometers. So here I have a simulation for a micron, but in reality, a 50 by a 200 nanometer device could store many states, like 5 states, 7 states, 11 states, and so on. But it cannot store a million states. So it is still kind of has a very finite and small resolution in the number of states that you can write. So in other words, if I write this magnetic state to this, physically move the magnetic domain that is pointing up or down to a different regions in space, right? Like this region versus this region versus this region, the resistance can be varied. So I basically have a programmable resistor, which is my synaptic weight. The thing is, once I come and get stuck in a notch or close to a notch, I'm going to remain there for a while unless that weight is perturbed again. So we then go into the physics of the write process, which I won't go into here. But what we see is when we drive this by a current or what we call a spin orbit torque to move it to a particular place, it goes there, but it doesn't really go exactly where you want, right? So you may want to write it to a particular position. It goes here and it gets stuck, right? But it may not always come and get stuck here. It may get stuck here sometimes, here sometimes, here sometimes, and so on. So the weight that you write or program is stochastic. Stochastic in the sense there is noise in it. It's not always the same. So this is the physical characteristic of the device, right? And then we are using this device here to store this weight. So there are two kind of caveats with this weight. Unlike in a traditional computing where you can have a huge floating point number with large accuracy, like a number like 2.35678, here you can only store a few states, maybe like -1, minus half, 0, half, 1. Yet with this kind of information, you want to be able to do very accurately classify or do other inference tasks, right? So the trick here is what we do with the level of the algorithm and the training is we take this device, which is inherently crappy. Crappy means it has few states, it's very noisy, it's error prone. But when I write this weight, then or write a few of these weights, then I again pass my data through this network and see what's the output, right? And if there's an error, I kind of correct the other weights around it. So though the weights are erroneous to some extent, you have constantly trained with those erroneous weight and the network learns to compensate for it in the long term. So if you use that, what we have shown is that if you have a floating point number which takes 32 bits of information with this kind of network topology and you train it, you can train it to test at some accuracy, let's say 97%. Now, if you reduce these number of states from very, very accurate to just two states, 0 and 1, with the same network topology, of course, you will see a drop in performance. Your accuracy is not good. But the moment you can store, like, say, -1, 0, 1, three states, it improves a lot. And by the time you hit about five states, which is -1, half, 0, half, 1 weight, you are almost close to the floating point, right? Not exactly there. There is some error, but the error is a little more, but you're almost there. So now that means with a network which has only 3 bits of information instead of 32 bits, you're still able to do inferencing at very high accuracy. And what is different here is we're just not storing 3 bits of information. We are storing it on a single nanoscale device, which has all these thermal issues, etc., because of which you don't exactly get the weight that you program. But in spite of this, this works well. In fact, the thermal noise acts as a regularizer and helps improve the accuracy and reach state of the art. So that's something which is very interesting. That is why these devices can actually be promising in practically to implement large networks. So we worked with a group in India. Again, this was Brajesh's group to show that it's not just the deep neural networks. If you put something like a convolutional neural network to do image recognition on the CFAR data set, you can again get very highly accurate information classification. And if you compare with the purely CMOS devices, you will see that you have a 14 times reduction in the chip area required to do this, 10 times reduction in the energy, and about 3.5 times decrease in the latency. So a little more, and we will talk about this anomaly detection. So we have looked into using these kind of ideas for anomaly detection as well. We have, with other groups, collaborated to come up with these actual nanoscale devices. Right now, this is a micron scale, but we would go down to nanoscale to show that we can control these domain walls to actually implement such devices. So in that context, there is another area that we have been working on, and this looks at information in a very different way. So if I want to encode a state of half, then I don't encode this now by a weight, but rather as a noisy pulse that is flickering like this. So if it stays up half the time and down half the time, it includes the value 0.5. So now if I have two random pulses which are either high 1 or low 0 half the time, and I multiply the two, the average probability that they will both be 1 together is half of half, which is 1/4, right? So in other words, you can have a simple NAND gate, or sorry, an AND gate, which ANDs this stream of information and this stream of information. As long as they are completely random, the noise is random and uncorrelated between them, the AND gate just implements a multiplication operation. Now, when you have negative weights and so on, so you can't use an AND, instead you use an XNOR. And what this does is then it multiplies these bipolar weights where your weights and outputs can be positive or negative. And then that information of that multiplication is stored in what's called a parallel counter, and then that becomes the input to your next neuron. And here again, we are shown that by using this quantization technique, where we use only 5 states or 11 states, we can get very high accuracy. So in this case, you don't have a long bit stream. You can make that bit stream very small, which means there's an increase in latency. Decrease in latency as well as in decrease in the amount of energy consumed, and you can get very good inferencing with this. So now I'll move base to another problem, and this is a problem where you have recurrent data. So in the previous case, you had an image, and the whole image was input to your network, and then you classified the image. But what if you have time series data and you want to work with that? So typically, when you have neural networks to deal with time series data, what happens is you have these, you, you need information at this point in time that is given now to interfere or mix with information that was given back in time. So let's say I have a paragraph, you have a word that you're speaking here, and this word is in the context of everything that was said before, right? So there needs to be a time element to it. And in traditionally in neural networks, people used to use what are called recurrent neural networks and LSTMs, etc., where you would have some memory in the system. But a physical device that could kind of use this memory is what's called physical reservoir computing. And let's take our example of magnets again. So I have a magnet here. I'm able to program this magnet and put some information that moves forward. Now, because I kind of perturb this magnetization, the next magnetization gets perturbed, and the next magnet, and the next magnet, and so on. So then, but when I perturb this magnet, this perturbs this, and this perturbation can come back here and interfere with information that is coming in, right? So in other words, it can do this, it can handle this time or recurrence uh, naturally. We don't need to train these weights. What you do is you just take these outputs and then do a linear regression on them to do a classification or a prediction task. So again, these are physical magnets which are smaller than the wavelength of light that we have fabricated in our lab using electron beam lithography, and then shown that we could have these frustrated states. We worked with an architecture group that actually put this very complex array of magnets and showed that it could do interesting digital tasks. In our group, we have also looked at a complex array of magnets where we put analog information, which is basically modulating this carrier frequency and inputting it to the magnets and showing that it could be used to process information. In fact, this system here has what are called requisite amount of short-term memory and parity check, which will allow it to process information. And indeed, it does process information or predict. For example, if there's a Meckie glass time prediction, you can teach it to predict the output or the next few steps of this differential equation by training it. If you train it with this information, it can predict what happens next. And the predictions for short terms are indeed really good. And that shows that it has that capability of predicting tasks. So the next thing is, what about spatiotemporal information? And this is a interesting question that we'll deal with later. But I also wanted to mention that a lot of this reservoir is not just theory. We also have experiments with samples grown by Kai Lu's group here, where we show that because of this immensely hysteretic and time sensitivity with respect to what happened previously in time, you can take these magnetoionic materials, train it with some information, and show that it is actually able to do reservoir computing. We won't go into the details today, so that's the experimental implementation. And what we are currently interested in working on is, look, if we replace these LSTMs with reservoirs, of course, they can do good temporal information, but then if you can also couple it with a convolutional neural network, can you work with information that has space and time? So that brings us to the end of the more futuristic work on actually using devices, nanoscale devices, to make AI hardware very efficient. But now we will talk about some other simpler, more practical things which we can do with existing hardware, right? So, for example, one thing that you could use, or one architecture of this network, is what's called an encoder decoder or an autoencoder, where you have an input layer where you which has information. You compress that information by progressively having smaller and smaller number of neurons in the subsequent layers till you have a bottleneck layer. So in other words, this information is transformed into another space where it is stored in very little, much lesser number of neurons, right? And then there is a decoding where you try to reconstruct this data. So what it means is, suppose I have something here that is moving, and it's supposed to move in this way. So I keep learning the way it is moving by wanting to reconstruct it from this input data, perfectly reconstruct the output, or not moving, but its states. So now if it does something weird, which is what we call an anomaly, it does something that it's not supposed to do, you have never trained it to on this. So immediately you're not able to reconstruct, right? So when the error between the output and the input is high, that means it is going to a state which it has not seen during training, which means there's an anomaly. And typically an anomaly can be a fault, which is a deliberate attack, which is like an inadvertent fault in the system, or an attack, which is a deliberate malicious attack on the system. So this is what you're trying to detect. And in this case, we look specifically at a communication packet. So again, this goes into the details of information that this is a dimensionality reduction, and then you're trying to reconstruct this. So and then the specific data we used was this NSL KDD data, which is for an information packet in communication. So we go into the details of how much training, testing, data, how all these different features are available in this data, how we encode them into into packets of information. And then so this is for example, normal, this is a malicious packet, but you really don't know the difference. But when you train it on thousands and hundreds and thousands of these normal packets, it gets used to the trend or the inherent features in that data. So when you then give a malicious packet, it knows that you're giving it something that is not correct, right? So we in the initial cases here, we wanted this stochastic weight. So we used micromagnetics and the magnet example to store it. But in reality, you could just implement this on an FPGA and get similar results. I don't include the FPGA results yet here, or the simulation results for that. But what the crux of the matter is that you can look at this very low resolution weight, you encode this information, and then you iterate, you change the thresholds, etc. And when you are sufficiently trained your network, you can show that you can actually make very high accuracy predict uh, classification of whether there was an attack or not, even with just 5 states with quantization, right? And as I said, the noise seems to help. So that is something which is harder to get in actual hardware against a nanoscale device, but nevertheless, this can be done. And one big advantage there seems to be is that when you quantize, or you have only few states allowed, you don't have to train the weight so many times. So you have almost 3 orders of magnitude, or 1,000 times less number of times you train the weights to still get your accurate results. So with this, I'm ready to summarize. So the summary is very short. You can do energy efficient computing, particularly AI, when you bring in these nanoscale magnetic or other nanoscale devices. But then you really have to have an engineering solution that bridges the materials, the devices, the circuits, and even the algorithms to get that maximum computing efficiency. And for more immediate, we could use quantization with existing hardware to solve a lot of interesting problems. And with this, I'd like to acknowledge all these grants. Some of the NSF grants were also used for the more hardware work. I mean, the devices work, and for the more applied work, we had the CCI funding, and also some breakthrough and other grants. Thank you very much.